Okay, good afternoon. I hope everyone has their ceramics and we're ready to go in terms of the final push today. After the lecture, I'd like you just to have stay here for a little bit so we can talk through what we're going to do tomorrow, because it's a little bit of an orchestration of moving all the work downtown to the medical campus, and then also just want to give you just some heads up on the presentation. We're really happy to have Jason Vollen and Matt Guildensparger come back. This is, I think, Jason has been with us all 4 years, which is pretty amazing. And it's very significant because I think this project in some way has grown with ACAW, and we have been in constant feedback back and forth from when it started, where it was in the first year. I know Jason had some prototypes that he had done on his own, but it was really, we were sketching it in one of the groups and talking about it, I guess unitization with Morris Ajami, and I thought that was like the beginning, and then the next year it was the first pass and then a second pass, and now we're really at a point where it's really complete. This one's also pretty interesting because it has a rigidized component to it, which I'm sure you're going to point out, so that's a nice bridge between the two. But I think it speaks a lot to what I think ACAW is, but also a real gratitude to Jason to stick with us in this whole process, and Matt for the incredible work that you put in and you bring back in terms of doing this. The prototype itself is really where we would love to see a lot of this work go. Obviously, in some cases, these will be just kind of first passes and then it will stay, but if there are ways to sort of really push this towards a product of this sort, I think that's really where ACAW can really shine in a slightly different way. So Jason's here to give us insight again on where the project is now, and I'd like to welcome him and Matt, and thank you for being here.
Thank you. First of all, I can't think you're thanking me, because there's so many people to thank. I have been very fortunate to be part of ACAW for 4 years. I think Andy was working with me in the first year where we first looked at extrusion as transferring extrusion as a method of developing what we call the thermal adaptive ceramic envelope, which has been a long time project that Matt and I have been working on for, I don't want to say decades yet, because it's like 1+, but we'll call it decades. And of course, I've divided this talk into pre-ACAW and post-ACAW, or during ACAW era. And I thought I'd have 10 slides, but I have 70. So I'm going to do the pre-ACAW really fast, as fast as I can, because I think it helps set the context of why. And I think from a design perspective, for us, you have to ask the question of why are you doing? What is the thing that gets you up to come back year after year to kind of do this work? So I'll try to go through this relatively quickly. And the kind of as a philosophical position, I always like to start with nature. Nature does nothing uselessly, right? So if we want to figure out how we solve something in the built environment, we often can find some sort of analog. And I don't mean that by biomimetics, but I think there's a natural analog that we can learn a lot from. And normally I would end a talk with this slide, which is something we did in the pre-ACAW era very early on. And I think we'll have the sound. You got to listen. Okay, that's a Stirling engine being run off the heat, transferring through phase change into the backside of the tile. So that was the first proof of concept in 2000. Matt, what would you say? 2012 or for 13. So we also like to call it camouflage, meaning that we're camouflaging the building to the climate. So climate camouflage, and in this case, we like to think of it as building the better brick. There's an evolutionary process that we envision that if not today, but maybe in 50 years, if a brick is sitting on a wall and it's not doing 2 or 3 other things at the same time, you'd find that troubling, right? So we want to be in the lineage of that, of developing that kind of thinking about what the building envelopes do. And part of the why is because this is what the world is affected by all the time, some form of climate. And energy sources that are dynamic and moving throughout the day. But how we need to view this as designers is in this terms. So it's not so much the exact quantities of things that we're interested in, and these tapes now are kind of commonplace and regular outputs. But what we're really interested in is in the volatility index how that energy is moving and how much is it peaking or valleying, and how can we take a stab at the peak and valley with the building envelope if we accept that 50% of the energy, more or less, is moving through the building envelope, and that's what our mechanical systems currently has to contend. So nature, of course, does nothing uselessly and has been doing it for quite some time. So the Alpine buttercup creates a parabolic shape, tracks through the growth in its stem and a blue light sensor, concentrating energy to the center of the flower so that it attracts insects first in its region, right? So the idea that we can concentrate energy and to thrive. Cactus maintain their water content by having a variety of techniques, including coloration, surface pattern, dealing with airflow. They're water bags in the desert, right? So they've evolved to be really smart. There's things we can learn there. And really the idea of the rete mirabilis, or the countercurrent heat exchange that we have, but are really well exemplified in the duck's feet, because in freezing temperatures, they're still able to maintain nutrient and fluid flow and core body temperature by using the principle of countercurrent heat exchange. So if we think of that as a primary context, and we say, how do we translate that to a building envelope? We've got a dynamic flow on the right side, and on the left side we've got the flow of the climate, and we've got to solve this with the building envelope, and we've been doing it for quite some time in a lot of ways, from mono-assembly and layered assembly, but the area we're really interested in is active and adaptive. How do we begin to take the energy flows from one side that are moving at one speed, and the energy flows on the inside that are moving at another speed? Historically, in the mono-assembly and layered assembly, we've done this by separating those two and saying inside deal with the inside, outside deal with the outside, and we're going to try to make a very tight building envelope. Passive house is largely based on those principles. Active and adaptive is a very different approach to that, meaning that we don't think that the building envelope should be the barrier to energy. It should be the way to capture, transform it, store it, and then redistribute it in a useful way. And this has been looked at over the past 40 years, first really captured by Mike Davies in the polyvalent wall, where each layer has a job to do and that they're collapsed together, and more recently by Ulrich Nack and Tilman Klein in the Facade Research Group, where Matt and I are engaged in, where they've looked at these types of energetic components that you can drive energy through the different types of layers in a multivalent wall. So it comes down to what types of principles are we working through? Well, there are a series of variables that come into play from a building. I know you came here for a building physics lecture, so we're going to start with this equation. No, the key point is that there's a series of variables. Some of them make a difference, and some of them don't make a difference. And we care about the ones that we think make a difference, and I'll circle back to that. So the challenge really is there's increasing pressure on finite resources. When peak, currently and for the next foreseeable future, when we hit peak energy in a lot of parts of the world, you fire up coal plants, right? So if you can move the peak to the valley and even out the building profile, that's the idea of the solution of climate camouflage that we can take into account with a kind of smart way of approaching this, in our case through thermal mass and ceramics, a way of balancing those thermal loads between the two sides without thinking of it as a question of keeping them separate, but more about how and in which way we bring them together. Right, so moving very quickly in the pre-ACAW era, we moved through a series of examples of taking those principles, and in this case, I would say an academic pursuit. Matt, you said it best, I think, this morning, where you said, this is the idea of taking ideas and making it like fit a wall section, right? But it's not real yet. And that's one of the things we began to work with techniques that have been used and have now been distributed around the world where they make plates. We've decided to make these like plates. And over the years, they became a little more structural. So this is the new ceramic CMU with a face tile that uses a lot of those principles. And then developed into a series of wall sections of varying degrees of integration and performance, transforming from what was a typical cavity wall brick to what we see as the replacement of that has the ability to resist lateral loading and deal with the thermal loads in a more intelligent way. Imagining that the world of that coloration begins to move in the true fashion of a camouflage. And so when we go back here, it's hard to see in the red, but there are a series of variables here that matter to us that are found in this prototype. So they found their way here by taking that energy that's moving from the two sides and capturing it So it could be increased surface area, flow rate, the thermal mass. And then we walked that through. And this is a prototype that we first did with Boston Valley Terracotta in the pre-ACAW era. I think it was 2000. John, we did this when? 2010? 2010 for the Integrate facade, AIA New York facade. So we built this prototype and brought it down, and it started to become more like a wall. And I think as we moved through this process to understand what it would take now to take it out of an academic exercise and into an exercise where you could think about it as deploying into something meaningful in the world to really tackle large surface areas and energy, we began to use those principles to say, well, let's begin building component parts of that. Again, the same variables in this version find themselves in the final version today, and it ended up coming right around the time that ACAW 1 came up. We were developing this prototype through Nexus New York, which is ultimately a NYSERDA-funded endeavor, and we were actually up here at the Rochester first cohort, and we came over and kind of restarted that conversation of how would we begin taking these ideas forward. And the next year, I think ACAW 1 started, and we sat down with knowing that we had been developing this system, which you see in this case is cast and can be cast or pressed, with an increased surface area, pin plate transfer. There's a fluid cavity here. Fluid moves in, moves past the transfer pins, and then out the other side in principle. And then we imagine that to be in some sort of wall section. Now, when part of the Nexus project was to interview architects, and we got some great feedback, like, that's a really big bunch of noses you have there on the side of my building. How do you expect me to design with that, right? So this is good feedback, right? So that's why you do 50 interviews and a process of trying to figure out how do you make it real, because part of it is the technical componentry of how we do this, which we feel we can tackle, and we can follow those lines to a result. But part of this is what will the market bear, and what will the decision makers bear? And in developing a new type of system that has an aesthetic to it, it requires all of the different fractured decision makers to come together. So it goes from manufacturing, what can we do with Rigidized and Boston Valley and the Glazing Institute, how can we put those things together? It goes from the owner, the architect and the engineer aligning that they would like to do this either the first time or that this is a meaningful endeavor to them. And ultimately, through the contractor, and the contractors gave us the same result. He said, if our subcontractors won't do it, we won't do it. So you have to go end to end from manufacturing to installer and line those things up. And so those interviews of what mattered to people started to shape where we began with this, I would say, in ACAW 1, where at the same time we started going through the ACAW cycle, we started doing testing on the module. So over the course of the year, we would be developing and testing and doing, in this case, physical testing and then modeling of thermal performance, and then come and try that out and see how far we got. So what you're looking at is in there that prototype, which we call the MVP, Minimum Viable Prototype 1. There's a series of 4 prototypes that we'll see through this next sequence. So this is a hotbox testing chamber, which is isolated to put a thermal load on one side, and then we're testing this. This is at Jefferson University in Matt's lab, where we're testing this. I think we had 54 thermocouples to get how much energy is going through, and this was really, I don't have the really good picture. This is like what we wanted to do, and then it found there was some sort of interference in the lab. So we went to Matt's basement, where it's thermally perfect. It's exactly the same temperature and humidity like all year round. And we built another one with wires everywhere, and that one really worked. We got some very good data off that. And what that data cycle does is help us to refine that. I'm going to take a bit of a pause here, because the idea of a thermal balancing envelope goes back really to the idea of the thermal panels. It goes all back to the hypocaust from Roman times, but if we look more modern times, this is from A.H. Baker, who really he patented these wall panels in the late 20s. And they were built in 1 or 2. It's very hard to find information on this. This was in England. They built 1 or 2 of these. You can see the pipes there. They're embedding them into walls. They would separate kitchens and living rooms in developments. What we see much more common, particularly coming to the US, and this is examples by Frank Lloyd Wright, is embedding those pipes into the floor. And you can see so now you have what we call thermal, you have a thermal what's called thermal tabs, thermal active building systems, which were largely, until very recently, thought of as a radiant slab, right? So you have pipes embedded in the slab, from houses to Johnson wax, so full range. Along this would say in the 40s and 50s, moving from the 50s through to today, they've been thought about in terms of transferring that energy in a variety of different ways, from void cavity to fluid, different types of chrome walls, partially active, embedding PVs. So the idea that you transfer energy to the building envelope is not new. Turning it into a product that is functioning that way is a little bit more challenging. So in prototype 1, which was coinciding with ACAW 1, we did a short-run production. So we started building these pieces out to do that testing that we showed in Matt's lab at Jefferson. And we made 16 of these with varying degrees of pin lengths. And from that, we began doing a series of models in Modelica with the Dymola interface, which is a Dassault system overlay that allows us to program the building physics and correlate that to the physical testing that we did, and then begin looking at those variables. So conduction was one of the variables that I talked about earlier. How long should it be a glued connection? Does it have to be a solid connection? It has to be it has to be a solid connection, not a glued connection. The flow rates and pin length, how fast should the fluid move through there? How long do the pins have to be? Turns out you don't need very long pins. You need a slight increase in surface area. And there's a nice story about how that aligns with rigidized as we move to the final prototype. The location of insulation, right? Real practical things. Where should insulation go? Do you want the energy to begin to wrap around to the backside of the tile and then radiate into the cavity, or do you want to try to stop that and focus it as much as possible into the working fluid so you can capture as much energy as possible? So at ACAW 1, we had a kind of discussion in our group. Morris was there. I think we talked a lot with Andy. We were talking a lot about this. I think Mitch, you hung out with us quite a bit. And a group of others where we started thinking about one of the issues was that we faced in the cast tile for us at the moment was two things. One, when we filled it with fluid, it leaked, right? It weeped out a little bit. So we had some challenges, like how do we deal with the fact that this is going to weep? That shouldn't stop you. You should keep going, right? The lesson is, okay, now we have a problem, but you keep going because you'll solve it. Put a pin in that one. We'll deal with that one in the next round. But what came out of that for me was I had a lot of time to sit and sketch how the system should work. And we did a range of tests to see how do you use this? Where does the energy go? And it turns out that the energy flows that we have in and around the building envelope would be really considered low-grade energy. They're a little bit higher and a little bit lower than the comfort zone. So it works by bringing that in and out, but it doesn't work if you dump them into a mechanical system. And when we modeled that, it turns out that we've done all of our mechanical system work for the last 100 years on firing up really hot or really cold temperatures, right? So that doesn't align with this strategy of bringing that energy carefully across the building envelope to use it and modify the temperature a little bit. So that's how you see the arrangement today, where you see a radiant and cooling panel on the backside of the system rather than dumping that energy directly into the mechanical system, because our current mechanical systems, except for one, which I'll get to, can't really use that. So in ACAW 2, we thought we would look at this in terms of moving to a more solid pressed piece, where we tried to attach the fins for thermal transfer here to the blank, which we called, in this case, proof of concept, prototype 2, where we attached a radiator tile to one side, and this tile, you see the front tile to the front, and we put fluid through it and some reptile heat lamps on it, very scientific, and turned them on as long as we could. And about 4 hours later, you could find both your hand, but also from the thermal imagery, that the heat was going, right? That's what POC, proof of concept. So it worked as a system. We could pull the heat off, we could put it into a storage chamber in between, and then we could pull it onto the other side. And these are some of the pieces where we were trying to make this monolithically. And where's Andy? Ann here, so I think I saw Ann before. Ann worked with us on this one from the early stages, so we were match made by John and Mitch, and so she came on board, and this should go to the next one here, where we worked with them on what the profile of that piece could be and how we could do end caps to terminate the end pieces. And they made a mold in their shop and began to extrude where we could do mock-ups, because we wanted to address the issue of what the thing looked like as well as how it performed, and see how we could align both of those things. So out of ACAW 2, this both idea of what the potential extruded aesthetic could be, as well as with the cast piece, we had proof of concept. And then we tested that through the course of the year between 2 and 3. And I think the key, this is cumulative energy over time. When you compare that to solar thermal and photovoltaic, depending on the inlet temperature of the working fluid, we are very similar to solar thermal in terms of output. Well, actually a little higher, says my graph, but I made the graph, so don't, I could have moved it up or down. So, and photovoltaic energy, which actually is significantly less than thermal, because in many cases, thermal is more valuable than electricity for the purposes of space heating and cooling. So if we don't have to transform it to electricity, we have a great deal of efficiency we gain. I'm not saying we should not do photovoltaic, but our first stop is keep the energy in as high a concentrated form before transforming it. And so these were very encouraging results based off of Prototype 1. And Prototype 1 said that we have a savings from a typical ASHRAE 90.1 curtain wall, almost 15% in heating, and almost 7% in cooling. So again, for a couple rounds of prototype and some testing, we found that to be encouraging. It wasn't 3% or 4%. This is out of the margin of error, so to speak. And that encouraged us to try to build prototype an ACAW 3, what we call the integrated, architecturally integrated system. So that last year, we wanted to deal with the fact that the water was weeping out of our bank, and Mitch had a few years ago said you should talk to the folks at Rigidized, because they have a really interesting thermal transfer pipe. And so we called and said, could you please send us some pipe? I think it was like 3 days before, because sometimes you organize like that. And they did supply the pipe to us, but wonderfully enough, and we were able to marry the two things together in the system at ACAW 3, where you see this does look like a strange science experiment here. These are the ends of the pipe coming out from the rigidized pipe, connected by a series of tubes that are moving into storage. You can kind of see the difference here as a comparison, because we did one in copper and we did one here in the rigidized pipe. This is embedded now directly with HydroCal, which is very similar properties thermally to the ceramic. So it gets a full seal around it with a complete contact to and a mechanical link to the pipe, and then insulated to the back, hung on the standard, this was very important to us, hung on the standard Boston Valley track, because we didn't want to have to invent that component. So everything was built to now get closer to how you would deploy it in the field. And we began putting those together, and in this case, based on what we did in ACAW 1, developed the radiator tile that would then, this is on the back side, we'll spin it around in a minute, that was then able to take the heat. And I think the key part of this, and you can kind of see where we ended up at the end of 3, was a rain screen assembly. And what was different than the other prototypes is this time we took the energy through a countercurrent heat exchanger, a flat plate heat exchanger, to a separate loop, to a storage tank, and then another countercurrent heat exchanger, and the pumps ran separately, so we could store, build the heat up, and then turn on and then distribute. And what we found is in about an hour, from one side to the other side, we went from 85 degrees to 108 degrees on the other side, just by using heat lamps on the backside, which, rough case, probably close to a hot day in the summer in Buffalo, what we were getting. And so the important part was, it wasn't the fluid transferring, it's the energy that was transferring and being stored and being delayed so that we could use it. And through the year, we then began to do the model between version 1 and version 3. And version 3 is very similar to what you see as the prototype. And you can see we've now doubled the heating capacity, but we didn't expect is that we also lowered the cooling capacity of the system. So I'll talk about why that we think that has happened. But it's a significant jump. So if we used to save almost 15% in heating, the new version models at saving 30% in heating, and that's not nothing. So we feel like, again, we're encouraged to continue down the line of having active fluid as part of an envelope strategy. And one of the primary differences that you see between version 3, which is modeled and similar to here in version 4, is the amount of heat transfer surface area in the pipe versus our previous amount of heat transfer surface area was significantly higher. So we have much less fluid, much less heat transfer surface area. The ceramic volume is somewhat similar between the two. The amount of working fluid is significantly less, and the proportion is quite different between the heat transfer area and the working fluid volume. And then you can see the difference in the outcome, significantly more heating, but still significantly more cooling. One of the reasons we feel that is because here the fluid was then moving in a large bulk mass through the outside of the tile. And in the case of the version 3, it didn't have that opportunity, so it's constantly heating. So the offloading didn't happen, so you're constantly heating in the loop. So that was something we put a pin in that until this year. And then in between, we decided to do ACAW 3.5 at Jefferson, because now that we were able to take a product that we felt like had some validity, working with Rigidized and Boston Valley and United Glazing, that we could take it out of rain screen and try to unitize this, thinking that that's a larger goal. You want to factory build this so that all of the pieces can be pre-tested and pre-plumbed if you've been out on site and tried to do an integrated system, particularly in New York, but in many places the amount of trades that have to come and the way that they have to come are very concerning, so that a unitized system will support the factory install and testing of most of these pieces and minimize the site time and the potential for problems in craft in the field, and shift that to problems in the factory that can be troubleshot before they get out to the field. So moving to a unitized system helped us think about how we would prepare ourselves for the prototype this year, which the intention was today, which was to show you a prototype and give you the history and how ACAW participated in that. And what we came up with was kind of a modular system, in this case where you can do a full glass panel, partial, stack, and by stack I mean there are 7 tiles in a row, that can get wider to a certain point at the limits of where we can do an extruded piece of about 60. We kept it at under 60 inches with end caps, and if we go farther than that, we have to begin linking them together. And why we wanted the variability is because we wanted to think about what does this mean ultimately if we cycle back out away from the engineering component of that, what does that mean from a design perspective? So in this case, we're able to look at the building facade in terms of window wall ratio from like 20, 40, 50, and 60% glazing, and get different performances based on the side of the building it is, going back to the idea of climate camouflage, that each bay, there's 2 bays in each one of these, can be made up of a series of modules, one of which in each bay contains all of the hardware to run that bay's system. So it's built base to bay upon bay. And then building this out, you can see here the extruded pieces, the rigidized components, the Boston Valley track, the thermal storage components, the radiator pieces in the back. It's missing the little pumps, but you can see those in the back after that. And then built that into the prototype that you're seeing here. And then how the rigidized piece is. And I was thinking how hard it was to think about building the rigidized components, drawing them, right? So Matt took all of this together, pieced everything, started working with Andrew. Was Andrew here? Andrew's been working with us for years on this every year, not here. So shout out to Andrew. She's back at the shop working, good for Andrew, right? And so that has to translate to what happens with the ceramic in terms of it's going through the manufacturing design process so that the shrinkage is kept intact. And I spent a long time vetting, all right, what do we do when it doesn't fit, assuming it's not going to fit, and we'll have to do this and we'll have to do that. And of course, they fit perfectly. And I thought, how lucky. And Matt reminded me that's called planning. So it was planning on all sides that allowed these things to go together relatively, I would say, easy in the way that we expected it would be. What's, I think, critical, and then they were up here being put together last week. So in the last, I just have a few more slides. I think one of the things that was interesting was our first idea was that that drove this as one of the principles, that increased surface area and flow rate will increase the thermal transfer and allow us to direct that more effectively so that thermal mass can be controlled and allow it to act dynamically. So it could feel like it's heavier or not heavier. When we looked at the rigidized product combined with the ceramic together, what we found was our pin plates as designed had similar geometric properties to the rigidized product. And hopefully I'll get this right, but I might get this wrong. And I think Chip and Jim and Dr. Dave have been really supportive of us in giving us technical feedback to program into our model how the thermal pipe works. That at the right flow rate, you increase the thermal transfer capacity of the pipe by about 10 times in a certain zone. And we can back end that into the system. So 10 times of a copper pipe with an increase of about 30% surface area. So for a modest increase in geometry, you can get a significant increase in thermal performance. And ultimately, that is the overall lesson that we could drive forward in many different ways, not just this system, but in many different ways. And so now we're about to try to model the two together and see how they go. We're pretty confident that we're going to see a big increase when we compare them. So right now, hot and cold really run through the same pipe. And this is where we're moving to, I guess, 4.5. And what we learned from the modeling, that the cooling capacity has to run through what's just been heated, is that we really need to begin separating the loops. So two alternatives, really cost-driven, where we have a separate heating and separate cooling loop, so we can offload and onload at the same time through the same tile. And really where we think we need to go is to have a assembled piece where we have an onloaded a heating loop tile and a cooling loop tile. And that's very important because in many of our buildings, the heating and cooling zones are running differently around the building at the same time. So you can imagine that they begin moving in some way that you can begin aligning these types of systems around the building. But as a fundamental system, your building can be in heating and cooling simultaneously, day by day, season by season, and year by year. And you want a system, when you're talking about truly adaptable, that can move between those. So you can do local radiation. But if you think about tapping into a Geo Exchange, the temperatures at Geo Exchange are very similar to the temperatures that you get at the building envelope. So of all the mechanical systems you could begin tapping into globally, if you have a Geo Exchange system, you then can tap into that, and you already have the delivery mechanism. The ultimate impact of that from a building's perspective is making the core of your building smaller. And for the perspectives of your clients and tenants, is that you get more usable space back when you put a lot of these systems of exchanging that energy to the perimeter of the building. So in our next kind of round, what we're looking to do is begin separating that heating and cooling so we can look at what does simultaneous heating and cooling do, offloading and pulling in, and then how would you begin modeling that around the course of the building envelope. So ACAW, what the pre-ACAW and post-ACAW era is for us was the ability to take things in principle and drive towards manufacturing for widespread deployment so that we could work with Omar, University of Buffalo, Riginize, and of course Boston Valley has been our anchor for decades in supporting us thinking about these things, but how would we do it for real? In many cases we were supported by dollars from our institutes. Both Matt and I were at the Center for Architecture, Science, and Ecology for many years at SOM. But more recently, moving from a kind of academic support really to industry support. And the acceleration when you move to industry support is significant. And that, from my perspective, why I started by saying I should be thanking you is I really have to thank ACAW and all of you who put this together, because it took what we thought was a good idea and turned it into something that we think can be a real product and is getting closer every year to getting there. So thank you all for that. So.
So do we have any questions? I got to run this to you.
You mentioned in the first year you worked with Ajami.
Yes.
Have you continued to work with him or other architects?
We've cycled back on where we were. We updated him sometime in, I don't remember when it was, Mitch. We went January. Just give him an update of where we were, saying we're getting closer, right, to where we're going. Yeah. I mean, ultimately, our goal is to get it, is to prove it in place in a building. So we think we're getting close to the point where we have the right relationships and right industry support, that another round, we're ready to test it, and then we'll need a site, right? So any volunteers? Anybody want to put their client really on the line for liquid moving across the building envelope?
John.
I think you missed Dr. Carty's lecture about phase 5, or what do you call it? Phase 4, we're talking about thermal massing with the ceramics, and we need to get you in dialogue on that, because I think we can get more improved performance out of the unit that is going to be taking the heat measurements, and we're excited about that, so stay tuned.
Yeah, I mean, I think there's so many areas, now that we have all the pieces together, to me, this is the newborn, right? It's so many different parts that we can look at, but you have to get them out there, and they have to leave the notebooks, leave the hard drives, and get into something, so you can really see what's going to go wrong and where improvements can be made, because then it becomes really clear, right? We can improve the clay body. That will add another few percent. And this is really a battle of percents. Each component, each variable improves it a few percent. So that's why you go back to Mike Davies and all those layers, each of those layers is contributing a few percent, but eventually you get to 30%, maybe 40%, which would be significant. And if you look at that from the sizing of the mechanical system, if you could cut down your mechanical system 20%, the capital cost savings would pay for the envelope. It's a simple equation. It's not a hard equation to do if you can get that far.
So Jason, I think you hit on an interesting point there, and you're talking about a specific value to the owner in this instance, and potentially to the designer. If you're developing something innovative, and you touched on it earlier, how do you bring the key parties on board, and in particular, what matters most to you, teammate, who I want to be engaged? How do you approach that, whether you're talking with manufacturers, owners, scientists, architects?
Well, the first thing is you have to do really good listening, and the process of the Nexus New York process, I'm not sure if I think they're still doing those rounds, was really good process for us to be involved in, which required us to do a business plan, which required us to pitch for venture capital, which no one in venture capital really wants to fund anything that you don't get a return in 12 months, and our return is like 7 years, so they really appreciated our presentation, but no thanks. But going through that process was really good, and part of that process is looking at the Stanford Lean business model, which is, the part of that is to do 50 interviews. And so in those 50 interviews, it's not for me to tell you I'm not trying to sell you what this is, I'm trying to listen to what's important to you. In some cases, it's certifications. I want to make sure that your system is going to help me get Passive House certified. In some cases, I want to be able to control the aesthetics. You can't stick out that far. I need to have more understanding of the control of that, right? The owner needs to either care a lot or own it long term, right? So if you kind of start to line those things up, if you interview 10 people, you're going to see the patterns, right? And so listening makes you ask better questions to those people, and then you find out where everyone aligns. And I think this is the result of that type of questioning over the 4 years. I don't know if that was an answer. Okay.
I have a question about the prototype. I'm curious about the vertical large box aluminum extrusions and their relation to the end cap. Is there a functional interrelationship going on there, or
The functional relationship was the curtain wall manufacturer didn't have the thin die complete yet, so they gave us the big one. So you could imagine the I mean, the post-rationalization is it's thermal, not solar, so it's fine, but this would be cut back.
Thank you.
Yeah.
Because
That's what you're wondering.
I think the end caps are beautiful,
Yeah.
but they're hidden.
Yeah, so they would.
So I wouldn't want to see that happen.
Yeah, the primary structure is back, so this can cut back in line, and that can stick out and get full exposure.
Speaking of hidden, can you turn it around?
Yeah. If it, see if we can get him there. I feel like Vanna. So in a unitized system, one of those modules across the bay can house the storage, all of the pumping, and the electronics, and the others are just collectors. So really, and enough, the storage for the entire wall in the amount of this size in phase change can deal with the whole bay. So it really is a fairly compact system. So only one unitized system per 30 feet has all of the major componentry. Everything else is connecting plumbing all the way through.
Jason, can you explain the rationale for datum elevation, like why that is where it is?
Right, so if you imagine this is your floor somewhere in here, putting the unitized curtain wall system, your connections are going to be above the floor for install, and then this becomes the ability to line up either below a window or get access to and pre-assemble these, because they'll be hoisted into place and placed down here. So imagine this here is your floor, that here is your sill height, and that's your typical radiator. If you do it in office buildings, you'll have the perimeter heat, potentially in residential as well. So that's going to be floating below that sill height. All of this being the kind of interstitial space. Imagine this is spandrel panel here to here.
Just one second.
Thank you. How will work the service for this over time? How you maintain this system, from the interior or the exterior?
So there's two penetrations per panel. There's an inlet and an output, and that stays static. So you service the outside. The end caps pop off using the Boston Valley system to reveal. You can see them on the backside where the pipes come through, and there's very few connections. And the same thing from the inside. So very similarly to any radiator. This is if you think about what's ready to go out the door, the radiator is largely done. I think in a month worth of work, we could turn this into a product viable for the marketplace because it's a radiator. And if you think of how many radiator choices you have as designers, there's like 10, and most of them are not so interesting. So we've added 10% to the choices that you have in ACAW of choosing radiators. And we're pretty confident that we're ready to roll on this very, very quickly. So that's something we're excited about. But in that case, these are all looped in. These can be, you see these connections here, we're thinking about a manifold, but also they can be mandrel bent. So the next phase is not to sweat and pressure test these connections, but to actually start with a single length and then bend them so that there's fewer connections so that you get 1 or 2 connections per. So as long as those are tested, the idea of maintenance, how many times does your radiator leak over the course of having a radiator? It's not often if it's been manufactured correctly, right? So it shouldn't need a lot of maintenance because it's fluid through a pipe in a building, and we've done that for 100 years. I hope. Hope is good.
Hi.
Hi.
When you are doing the calculations to show your performance over ASHRAE and reduction in energy consumption, are you assuming certain programs for the interior of the building and certain climactic zones for the exterior? And Have you found that this performs better in certain situations than others?
I took that slide out. Dang. Yes, it's a New York climate. It's really New York, modeled in New York City. We've also modeled Netherlands, and we've modeled Phoenix. And we have the comparison between those. And we've modeled this as office. So modern, typical open office space bays to start with, because we think that from a unitized perspective and a building commodity perspective, we're short on Class A healthy office space that is responsible from an energy perspective. So we feel like there's a lot of surface area that we have. Plus, the deep energy retrofits are probably the biggest market of all, and the ability to take off the facade and put a new mechanical system in, but in this case, put a smaller mechanical system in because you're putting on this new facade might make sense. So we started with that office space as the beginning.
Can you tell people in New York City how much money they're going to save on fines?
Right, yes.
Hi. So what type of fluids have you tested in this as far as for heat transfer? Because water works fairly well for a lot of things, but have you found anything that works better?
We have not. That's one of those areas where we would, from a building physics perspective, we can trip that in the model and change the fluid. We went with water because it's known and understood. It's an easy one that everybody can agree on. You could replace it with glycol, which will give you a similar type of effect, and then deal with the fear of freezing, which people will have on this. So, down the line, we thought about a phase change slurry to support even more. So microencapsulated phase change in a slurry moving into the tank could augment that, and building the physics model of that will take some doing. So we didn't want that to hold up the process, but I think that's one of those areas that we could build more a couple more % out of, getting the right fluid dialed in.
Super interesting. I'm curious if your conversations with facade subcontractors, installers, where they have gone to, and if you have any sense of clarity on how the whole sort of responsibility of performance, sort of warranty aspect of thing would work, as to how far are subcontractors who typically take the full warranty of the performance of the system, how far they're willing to go with it.
If I had to game this out, I would say you would have to do a design assist with your facade contractor, and they would have to own it. As the important part of this is that the system is largely separate from the environmental barrier. It's 2 penetrations, which happen all the time in buildings. So this whole component is warrantied by the curtain wall manufacturer and should continue to be, because it's not affected by this system at all. Who would own the demarcation from a liability perspective? I think you have to work that out. Matt and I have commercialized things before and gone through the process, and it's just it can be done. It's just a lengthy process to put in the right, and you pay a lot in insurance to try to get a new system out the door. But that you can work it out. You kind of have to have everybody sitting at the table and making a decision about who's going to own what piece. But largely, we wanted to leave these pieces alone. We don't touch that, and there's no reason to void the warranty from that perspective. But that's also why we want to go unitized, so someone owns it going out the door as a tested piece of equipment, like a refrigerator, that then gets assembled on site. Yes, we started to last year, and we're going to see. I think we're going to probably shift over, just because people have moved around in their companies, and we'll probably be shifting again this year. I think we've worked with United Architectural Metals this year to put together these pieces. We're going to have to figure out who wants to own and deliver from the next perspective.
So to expand on a question that was asked a few questions ago about the modeled energies with using this system, were you using the data that you got from your mock-ups that you did to ACAW, or were you utilizing performance within the type
I know what you're saying.
with its inherent inefficiencies, right? Not the,
Yeah.
not the boo-boo on a unitized assembly, but like there are inefficiencies there that may not be captured in the kind of pure markup during the ACAW test.
How we did this was we worked with Justin Schultz, who is really our programmer from the performance side, who we worked with at Case for many years, to build the building physics into in Dymola, in Modelica, into the Dymola interface. And with those, we went through a process of taking the data that came off of the model, like the one piece that we tried, which would be the pure performance piece. We did CFD. We corrected for that. We corrected for a bunch of things. We tried to do some fit curves to make sure we were confident and derated that. Then built that into Modelica, and then so that you had a single unit in Modelica. Built that into a stack, and then captured that in a functional mock-up unit, and then brought that into Energy Plus. Replaced it in Energy Plus. So in the Energy Plus, when it goes into the functional mock-up unit, we have an understanding, because we have the weather file in there, and we have the basic understanding of how it functions per surface area of tile as separate from the parts that aren't tile. And so in Energy Plus, it takes this as separate from this. So it's not perfect. It's not doing the interaction between yet, but it is doing dynamic thermal calculating in Energy Plus, which was the goal, with try to get closer to how it would actually perform. So and it takes into account, part of the process here was to take into account all the ceramic that you need for the edges that don't contribute to the system, and all of that reduction in surface area from a pure square. So from a pure square perspective, it's very efficient. But when you start adding in all the pieces that don't work and all of the bleeding, thermal bleeding, you get less and less. So we tried to account for that as best we could. What we'd like to do, I think we're at the place where modeling isn't helping more now. What we need to do is get this running and test it again and say, what's our input and output here, and then recalibrate the model now that we've made these changes. That I think is our process going forward.
Great, thank you so much, Jason.
Thank you.
So what